So we're going to talk about properties of logarithms. So some properties of logarithms that we can use to help us. We'll get to where we're solving logarithmic equations. So the properties of logarithms are going to help us with that. So we're in section 3.3. And the first property we're going to talk about is the change of base formula. Some of you may already know this, but if you've tried to calculate logarithms on your calculator, and several of you asked on Friday, our calculators will only calculate the logs for two bases, base 10 and base e. So that's all our calculators know how to do. So we're going to figure out how we can calculate logs of other bases. So if we have AB and x, and all three are positive, and we have A is not equal to 1 and B is not equal to 1. So we don't want our logarithmic function, our exponential function, to be base 1. We want some other base. So if we have log to the base A of x, and we want to switch that to some other base. This is some base that our calculator won't calculate. To switch to any other base, we can use the change of base formula. And that's what we're talking about here. I guess I could put this up here at the top. This is our change of base formula. Log base A of x is log base B of x over log base B of A. So we have base A, and we want to switch to base B. So we're switching from base A to base B. So this is our formula that we use. The log base A of x is the log base B of x divided by the log base B of A. Now normally we want to switch to either log base 10 or the natural log, because that's what our calculator can calculate. So the formula for those is we're going to say log base A of x. A is just some number. Base 2, base 4, base 3.5. Some number is going to be log of x over log of A. This is base 10. Or that's the same as the natural log of x over the natural log of A. And remember, our natural log is base e. When we don't write a base, we understand that that's log base 10. That's our common logarithm. So this will let us switch from any base to a base that we can calculate in our calculator, or to any other base that we're interested in. So we're switching from base A to base 10, to base E, or to base B. And all three of these, if I wanted to switch to base B, I can put this down here also. This is the same as the log base B of x over the log base B of A. And if we calculate these out, these come out to be exactly the same number. The change of base formula will give us the same base no matter or the same number no matter which base we decide to change to. Because the log base A of x is just a number. So no matter which change of base formula we use, we can get the same number. So we'll look at a few examples of this We'll talk about some other properties of logarithms, and then we'll be able to see where the change of base formula comes from. Questions before we do examples? All right, so let's look at some examples of changing base. Pretty easy, pretty straightforward. If we have the log, if we want to evaluate, so your problem will say evaluate. Evaluate means come up with a number. So if we want to evaluate log base 5 of 18, our calculator won't do log base 5. So we need to do our change of base formula. Log base 5 of 18 equals the natural log of 18 over the natural log of 5. That's plugging into our change of base formula. Yes? I could, this is the same as, you can choose either. This is the same as log 18 over log 5. So either of these we can plug into our calculator and calculate. We can calculate the natural log of 18 and the natural log of 5. Divide those two. Same with the log base 10. If we plug that into our calculator, either one, we get about 1.7959. And this is an approximate answer because I rounded a little bit. So either of those are going to come out the same. Either of those are going to give us this number. And remember, this is telling us that 5 to the 1.7959 power equals 18. So if you plug any of those into your calculator, you should be just about right. So we know that 5 squared is 25, so it has to be less than, our exponent has to be less than 2. So it has to be between 1 and 2 somewhere. So either of these, we can pick natural log, we can pick log base 10, either one will work. I usually pick natural log because natural log is the one that you end up using more in science and in calculus. You usually use natural log, it comes up a lot more. So let's look at a couple more of these, just so we have an idea of how to do these. So log base 2 of 42. This is going to be the natural log of 42 divided by the natural log of 2. And that's going to be the same as the log of 42 over the log base 10 of 2. And when we plug that into our calculator, you should get about 5.3923. Either one of those should come out to be about the same. And this is the same as saying 2 to the 5.3923 power is approximately equal to 42. Let's do a couple more of these real quick, just so we are sure how our change of base formula works, and then we'll talk about some more properties of exponents. Or I'm sorry, properties of logarithms. So another example, we want to evaluate log base 7 of 4. That's the same as the natural log of 4 over the natural log of 7, or the log of 4 over the log of 7, and that's approximately equal to 0.7124. If I plug these into my calculator, this is what I get. And that tells us that 7 to the 0.7124 is approximately equal to 4. And we'll do one more. Log to the base 1/4 of 5. That's the same as the natural log of 5 over the natural log of 1/4, or the log base 10 of 5 over the log base 10 of 1/4, and that's approximately equal to negative 1.1610. And that's telling us that 1/4 to the negative 1.1610 is approximately 5. So questions on change of base. The hint on change of base is your problem is going to say evaluate, and your exponent or your number and your base are not going to be powers of each other. If you have something like on our worksheet, it would say something like evaluate log base 2 of 4, and you know 2 squared is 4. You don't need to use your calculator to do that. You know that because you know how exponents work. But if we know that we can't raise 7 to some easy exponent to get 4, that's going to be our clue that we have to use our change of base formula. And the problem may, if it's a problem where you don't use your calculator, the problem may also ask you evaluate this expression without using your calculator. That's going to be a hint that it has something to do with the exponents, easy exponents of your base. The questions on change of base. And we'll talk in just a minute about where the change of base formula comes from after we talk about our other properties. All right. So our properties of logarithms. This is what we're going to use to actually solve problems with logarithms and solve equations that involve logarithms and exponents together. Our properties of logarithms come from the fact that our logarithms are talking about exponents. Remember that we said y equals log base a of x tells us it's exactly the same thing as a to the y equals x. Those two are the same thing, logarithmic form, exponential form. So y is an exponent. So logarithmic functions are telling us about exponents. So our properties of logarithms come from our properties of exponents, because what we're talking about here are, in fact, exponents. So let's look at our properties. Our first property, and we're starting y equals log base a of x. Log base a of u times v is log base a of u plus log base a of v. We can split up, when we're taking the logarithm of a product, we can split it up into a sum, into adding. And for these problems, u and v are positive. Because we have to have positive numbers in our logarithmic function. So if we have a log of a product, gives us the sum of the logarithms. So that's our first property of logarithms. Just like when we are multiplying two numbers that are raised to an exponent, if we're multiplying a number that's raised to two different exponents, we add the exponents. It's the same idea. Our second property, the log of a quotient. Log base a of u divided by v is log base a of u minus log base a of v. So when we're looking at a number raised to an exponent divided by that number raised to a different exponent, we subtract the exponents. It's the same thing going on here. Because y is an exponent, We subtract them. Our third property.
Do U and V have to be positive for that too?
Yes, u and v are positive because we always have to put a positive number into our function. So log base a of u to the v power is v times the log base a of u. So when we raise a number to an exponent, we raise that whole thing to another exponent, we multiply the exponents. We're multiplying the exponents here.
Wait, so is that v log base a of u?
V log base a of u, yes. So this exponent here comes down in front. So these are our properties that we're going to use with logarithms to solve problems and to solve equations involving logarithms.
So are we going to have these on the test?
What's that?
Are we going to have these on the test?
Are you going to have? No, you need to remember these.
That's why.
Couple of easy mistakes to make, and I'm going to put these in red because I don't want you to make these. Log base a of u plus v does not equal log base a of u plus log base a of v. This doesn't work. We can't split them up like this. And the same thing with subtraction.
So what would you do now?
We couldn't do anything else here. If you had log base a of u plus v, that's you couldn't simplify it any more than that. We have to be multiplying or dividing here in order to split them up. Same thing with subtraction. Log base a of u minus v does not equal log base a of u minus log base a of v. It's a very easy mistake, a very common mistake to make. So I want to remind you not to do this. We have to be multiplying or dividing to split it up. And it doesn't go either direction. So if we have something like this, it turns back into this, not into this. So let's look at a couple of examples, and then we'll talk about where the change of base formula comes from, how we're going to use these properties of logarithms. We'll be practicing with them today, and then for our next lesson, we're going to actually use these to solve some equations. Any questions before we go on? Okay. First example, we want to expand. That's our problem will be expand, simplify, something like that. So we're going to expand the log of 2x to the third, y to the fourth. So we have a bunch of numbers multiplying each other here. So our properties of logarithms tell us we can split this up into a sum of logarithms. So this equals, I'm going to split it up into a sum, log of 2 plus log of x to the third plus log of y to the fourth. So I've expanded it. Now I have a log of a number to an exponent. I can bring those exponents down. So this is log of 2 plus 3 log x plus 4 log y. And that would be our answer to this expression expanded. So this is one reason why working with logarithms are kind of nice. Logarithms turn this multiplication into an addition problem. Turn these exponents into numbers that are multiplying rather than exponents. So this is one reason why logarithms are useful in solving problems. They turn multiplication into addition, and they turn exponents into multiplication. So let's look at another one. We're going to do several examples of this type of problem. So we have the natural log. Before we move on, anybody have any questions on why I did what I did here? All right, so natural log of square root of x plus 5 over y squared. And I want to expand this. Well, here I have division, and my properties of logarithms tell us we can turn that into subtraction. So this is natural log of the square root of x plus 5 minus the natural log of y squared. What is the square root? How can I write the square root as an exponent? 1/2. So this is the same as the natural log of x plus 5 to the 1/2 power minus the natural log of y squared. Well, now I have logarithms of numbers raised to exponents, so I can bring those exponents down. So this is 1/2 the natural log of x plus 5 minus 2 natural log y. So I brought those exponents down. And our hint here is, I'll write this in red, we need to remember that square root of x is the same as x to the 1/2. The third root of x is the same as x to the 1/3. So when we have roots, it's exponents as fractions. That's what I used here. So the other type of problem that we'll do with using properties of exponents is condense an expression. So we expanded these. We're going to go the other direction and simplify. We're going to make our expressions more compact. Questions before we move on from this? So for the next two examples, we're going to condense. Whoops. So we're going to condense 2 log x minus 3 log y plus 1/2 log z. So we want to condense this. We want to make it into one logarithm. That's another way that the problem may be asked. It will say write this expression as a single logarithm. So we want to combine everything together. So what's the first thing that we can do here? Anybody have an idea? What's that? Raise them. We have numbers multiplying, so we're going to turn those into exponents. So this is going to be log of x squared minus log of y to the 3rd plus log of z to the 1/2. Now we have these two logs subtracting each other, so what does that tell us? We're going to divide. So that's log of x squared over y to the 3rd plus log of z to the 1/2. Now we have these two adding to each other, so what does that tell us we can do? Multiply. So that is log x squared times z to the 1/2 over y to the 3rd. And that would be my logarithm condensed or written as a single logarithm. We could write this as a square root of z. We could do that and that would be fine also. Is there a question?
Why are you multiplying on the top? Could you just write it outside of Yeah, but that would still be the same thing.
Right, we can't write it outside of the logarithm, but we could multiply the z anywhere.
I think he's just saying outside of the denominator fraction.
Oh, sure. We could write this as, if you wrote this as log of x squared over y to the third times
Yeah,
z to the 1/2.
but dude, just do that. If you do it over 1 and then you multiply
Right.
that out, it's still the same.
Right, so I'm just saying that's just over 1. This would not be wrong. This would not be wrong. This would be fine. I just kind of combined them together. All right, let's do one more of these, and then we'll talk about where the change of base formula comes from. And then we'll be done. So we're going to condense this next one also. So we're going to condense 1/3 2x, 2 natural log x minus 4 natural log y minus natural log of z plus 2. So my 1/3 is out here in front of the entire parentheses. So we're going to deal with that last. We're going to deal with what's inside the parentheses first. Now to make this easier, I'm going to write this as 2 natural log x. I'm going to factor out this -1. I think it's going to make it a little easier to work with. Minus 4 natural log y plus natural log of z plus 2. So I just factored out a -1 from each of these and put these in parentheses. That's going to make it a little easier to deal with. So let's deal with the inside. I need one more parentheses there also. One for this and one for the 1/3. So let's deal with this inside parentheses first. So I'm going to write 1/3 times 2 natural log x minus, what can I do inside here? Natural log y to the 4th. This is multiplying, so I can raise that y to the exponent. Plus natural log of z plus 2. Now I can write 1/3. What can I do with this natural log? Natural log of x squared. Minus, inside my parentheses, I have these two added. So what does that tell me I can do? Multiply. So that's natural log of y to the 4th times z plus 2. And now I have this, I still have this 1/3 out here that we'll deal with at the end. I have this natural log subtracting this natural log. So divide. So this is natural log of x squared divided by y to the 4th times z plus 2.
Isn't it negative? Oh,
And I'm going to rewrite this. I'm going to put the natural log out front here. And this 1/3 in front of my natural log, what can I do with that? Yes?
how'd you get from that last step to the center on that? You just divided it.
Our properties of logarithms tell us when we're subtracting two logarithms, it turns it into division inside the logarithm. So what did we say this 1/3, we can do with this 1/3? We raise everything to the 1/3 power. So this is the natural log of x squared y to the 4th times z plus 2, all to the 1/3 power. And if I wanted to, this would be fine. Or if I wanted to, I could write this as the natural log of the 3rd root of x squared over y to the 4th z plus 2. Either of these are the same and would be fine. So this, if we condense this, This is what we get. So when we expand, we want to write it as adding and subtracting. When we condense, we want to get it all into one logarithm. Questions on that? And this is what the homework's going to look like. It'll say expand, it'll say condense, it'll say simplify. And we'll do some change of base stuff too. All right, let's look at where the change of base formula comes from. One of our properties of logarithms. So this is why change of base works.
Mr. Peter, could you go back to the last one really, really fast?
Uh-huh.
Thanks.
Mm-hmm. Why change of base works. We said one of our properties of logarithms was log base a of u to the v equals v log base a of u. That was one of our properties of logarithms. So let's say from here, let's say we have y equals log base a of u to the v. Actually, that's not what I want to say. Let's say that y equals log base a of u. So I'm going to rewrite this in exponential form. A to the y equals u. I just rewrote this in exponential form. Now I'm going to take the natural log or the log base 10 of this. I'm going to say that the log of a to the y equals, I'm just taking the log of both sides, equals log of u. Properties of logarithms tell us that y log a equals log u, or y equals log u over log a. So this is what I'm doing to do my change of base formula. This is my change of base formula. I have the log base a of something. I can turn it into the log base 10 or log base e using this property of logarithms. So that's why it works. You won't necessarily have to know this. I just thought it was it's nice to know that it comes from this property of logarithms because we talked about using that. All right, questions? Okay, homework. Our homework is 2 parts, part bookwork and part worksheets. One through 77, every other odd, and then plus our worksheet. I'm going to pass out the worksheet, and I want to do a couple of the problems from the worksheet together, so you have an idea of how to do them. So on your worksheet, let's look at number 1. This is in the section that says exponential equations not requiring logarithms. So number 1 says 4 to the power of 2x plus 3 equals 1. So on these, we need to use what we know about exponents. What exponent, if we raise any number to what exponent gives us 1? 0. The only way to get 1 when we're raising a number to an exponent is raise it to the 0 power. So this tells us that 4 to the 0 equals 1. So 2x plus 3 has to equal 0. That's what this equation is telling us. The only way to get 1 is to raise 4 to the 0 power. So 2x plus 3 has to equal 0, and we can solve for x. And that's easy. So that's one type of problem there. Let's look at something like number 7. Number 7 says that 6 to the negative 2a equals 6 to the 2 minus 3a. If we raise a number to two exponents, what's the only way that they're going to be equal? What's the only way that both of these, the two sides of this, are going to be the same? The exponents have to be the same. We have to raise 6 to the same exponent. This tells us that minus 2a equals 2 minus 3a. And we want to solve for a. The only way this is going to be equal is if our exponents are the same. Let's see. There are several like that. Let's look at something like number 10. Number 10 tells us that 2 over x, or I'm sorry, 2 to the x over 2 to the x equals 2 to the minus 2x. What's 2 to the x divided by 2 to the x? 1. So 1 equals 2 to the minus 2x. What's the only way to get a 1 if I'm raising a number to an exponent? The exponent has to be 0. So this tells me that 2x, negative 2x equals 0, so x has to equal 0. So that'll get you going on some of those problems. They look more complicated than they are. Use what you know about exponents. Yeah, these problems go really fast. The first 24 just change a base. You just use your change of base formula, plug those into your calculator.